Chapter 8, Quantities in Chemical Reactions. Let's consider the combustion of a fossil fuel, such as gasoline, and this produces carbon dioxide. Although gasoline is a mixture of hydrocarbons, octane, C8H18, is a major component. The balanced equation for the combustion of octane is 2 molecules or 2 moles of octane, 25 moles of oxygen, 16 moles of carbon dioxide, and 18 moles of hydrogen. This balanced chemical equation shows that 16 moles of carbon dioxide are produced for every 2 moles of octane burned. Since we know the world's consumption of fossil fuel, we can estimate the world's annual carbon dioxide production using the balanced chemical equation. It is known that carbon dioxide is a greenhouse gas, contributing about 20% to global warming effect. So reduction in the burning of fossil fuels can reduce the amount of carbon dioxide emissions. The balanced equation enables us to determine the amount in a chemical reaction. Stoichiometry, that relates the amounts of different compounds in a balanced chemical reaction. The stoichiometry are the numbers in front of the compounds in a chemical reaction, the coefficients that are required to balance the reaction. These numbers are called the stoichiometry. We can predict the amounts of products and the amounts of reactants from a balanced equation. Chemical reactions, mole-to-mole conversions. In a balanced equation, we have the recipe for how reactants combine to form products. Consider the following: hydrogen and nitrogen combining to form ammonia. The balanced equation shows that 3 molecules of hydrogen react with 1 molecule of nitrogen to form 2 molecules of ammonia. We can express these relationships as ratio. There are 3 hydrogen molecules to 1 nitrogen molecule to 2 ammonia molecules. This is a count ratio. We could say 3 dozen hydrogen to 1 dozen nitrogen to 2 dozen ammonia. But since we do not ordinarily deal with individual molecules or with a small number, we need to deal with Avogadro's number, a mole. So we can express this relationship as 3 moles to 1 mole of nitrogen, 2 moles of ammonia. This relation, it can be useful now for us calculating converting from one substance to another in a balanced chemical equation. Suppose if we have 3 moles of nitrogen and more than enough hydrogen. It's important to say that you're not going to run out of hydrogen. How much ammonia can we make? Well, this is a simple conversion. We simply consider the moles of nitrogen given. We look at the equation and we see that there are 2 moles of ammonia to 1 mole of nitrogen. This relationship is given from the balanced equation, the stoichiometry. Solution then looks like this. Begin what was given, 3 moles of nitrogen. Convert it to, using dimensional analysis, 2 moles of ammonia. Do the calculation and you have 6 moles of ammonia produced from the nitrogen. In chemical reactions, oftentimes we're more interested in mass-to-mass conversions. So a chemical equation contains conversion factors between moles of reactants and moles of products, but we would like perhaps to know what mass of reactants will produce what mass of products. The general outline for this type of calculation involves a series of conversions. Like we begin with the mass of A and convert it to moles. Of course, we do this by using the molar mass from the periodic table. And then these moles of A's to moles of B will be used from the ratio, the stoichiometric ratio of the balanced equation. Then moles of B to mass of B, again we use the periodic table and the molar mass. What mass of carbon dioxide is emitted by an automobile per 5.0 times 10 to the 2, or 500 grams, of pure octane? The balance equation gives us a relationship between moles of octane and moles of carbon dioxide. So before using that relationship, we must first convert the grams to moles. This is done. We take the grams of moles and apply the molar mass. We did this by looking at the periodic chart and adding up 12 times the weight of carbon plus 18 times the weight of hydrogen. Got 114.3 grams as a molar mass. Using the stoichiometry, 2 moles of octane to 16 moles of carbon dioxide. And finally, once we have the moles, using again the molar mass, 1 mole of 44 grams, to convert. Here's the actual conversion done. Given, arranging the conversion factors, so in the first step, divide by the molar mass and multiply by 16, divide by 2, and then multiply by 44. And you end up with 1.4 times 10 to the 3 grams of carbon dioxide produced. Let us consider a concept called yield. Actual yield and percent yield. The actual yield of a chemical reaction is determined experimentally. You actually weigh what amount of product that you get. And this depends on the reaction conditions. The actual yield is almost always less than 100% because some of the product doesn't form or the product is lost in recovering it, etc. Let's consider some of the important terms in this chapter. Limiting reactant. That's the reactant that's completely consumed in a chemical reaction. So when you're determining theoretical yield, you must know which of the reactant runs out first. You can't make any more product than if that's used up. Doing this calculation will give you a theoretical yield. Measuring the yield will give you actual yield, and the percent yield will be the actual yield divided by the theoretical yield times 100. Let's take an example. Let's consider titanium reacting with chlorine to form titanium chloride. Suppose we have 1.8 moles of titanium and 3.2 moles of chlorine. Which is the limiting reactant? Well, the best way to do this is figure out how much each one would produce. So we take our moles of titanium and convert them to the product. And we can see it's 1 mole of titanium chloride with to 1 mole of titanium. Or we take our moles of chlorine given and convert it to, then we compare the two, and whichever smaller is the limiting reactant. Here's this calculation. If we start with 1 mole of titanium, we get 1.8 mole of titanium chloride. If we start with 3.2 moles of chlorine, we get 1.6 moles of titanium chloride. This is the least amount of product produced, and therefore this is the limiting reactant. We run out when we reach this amount. We don't have enough chlorine to make this amount. In many industrial applications, the most costly reactant, or the reactant is the most difficult to remove from the product, is chosen to be the limiting reactant. When working in the laboratory, we measure the amounts of reactants in grams. To find the limiting reactants and theoretical yields from our initial masses, we must add 2 steps to our calculations. For example, we have sodium chloride. In this balance, sodium plus chlorine to make sodium chloride. We start out with 52.3 grams of sodium and 68.5 grams of chlorine. What is the limiting reactant and the theoretical yield? Well, we just begin simply by our usual map. Start with the given grams of sodium chloride. Use the molar mass given grams of sodium. Use the molar mass to convert to moles of sodium. Looking at the equation, stoichiometry, 2 moles of sodium to 2 moles of sodium chloride. Now we're into moles of sodium chloride. Use the molar mass to convert to grams of sodium chloride. Again, we can start with the 65.8 grams of chlorine, convert that to moles using the molar mass, convert using the stoichiometry, convert that to moles of sodium chloride, and then using the molar mass, convert it to grams. The smallest amount will determine the limiting reactant. Here are the calculations. (53.2 grams of sodium can produce 135 grams of sodium chloride. 65.8 grams of chlorine can only produce 108 grams of sodium chloride. Therefore, this is the least amount of product, and the chlorine then is the limiting reactant. The theoretical yield then is 108 grams of sodium chloride. The actual yield is usually less. And suppose you want to know then what the if you carried out this reaction and you got 86.4 grams of sodium chloride, and you could have gotten 108 theoretically, then the percent yield is 84 grams divided by the 108 times 100, 80% yield. Here's another example, 8.6. Copper 1 oxide plus carbon will set free elemental carbon and carbon monoxide. This is the balanced equation. Suppose you have 11.5 grams of copper 1 oxide and 114 grams of carbon. What's the limiting reactant? Again, you have to start with the grams of carbon. Use the molar mass to convert to moles of carbon. Use the stoichiometry to convert to moles of copper. Use the molar mass to convert to grams of copper. Or start with the copper 1 oxide. Use the molar mass to convert to moles of copper 1 oxide. Use the stoichiometry, 2 moles of copper to 1 mole of copper 1 oxide to convert to moles of copper. Use the molar mass to convert to grams of copper. The actual calculation, these relationships are used. Kind of repeat them, that a mole of copper is 2 moles of copper. You can get that from the formula really, but you can look in the balanced equation. 1 mole of carbon is 2 moles, and these are the molar masses calculated from the periodic table. So, to follow out our example, if we have 11.5 grams of carbon, converting it to moles, stoichiometry to copper, and molar mass, we get 122 grams of copper. If we start out with 114 grams of copper 1 oxide, converting that to moles, using the stoichiometry and the molar mass, we get 101.7 grams of copper. That's the least amount. Therefore, the theoretical yield of copper is 101.7 grams of copper. In this example, suppose we actually only got 87.4 grams of copper. Then the result is that from our theoretical yield we got less than we expected. So the percent yield is considered the 87.4 grams divided by the theoretical yield times 100 to give us 85.9% of copper. Last, let's take a little look at heat, which is kind of an invisible substance in the chemical reaction. Chemical reactions can be exothermic, that is, they give us off heat when they occur. Heat given off has a negative sign. Chemical reactions can be endothermic, they require to absorb heat when they occur, and heat absorbed is a positive sign. The sign of delta H, a change in enthalpy or change in heat content, is positive or negative. Depends on the direction in which the thermal energy flows when the reaction occurs. Energy flowing out of the chemical system is like a withdrawal from the bank. It's a negative sign. Delta H is negative. Energy flowing into the system is like a deposit. Carries a positive sign. Endothermic reactions have a positive delta H. Delta meaning the change in heat content. So let's remember stoichiometry. A balanced equation gives quantitative relationships between the amounts of the reactants and products. The quantitative relationship between the reactants and products, the little numbers used to balance equation, is called the reaction stoichiometry. We have talked about yields, limiting reactant, theoretical yield, and percentage yield. And it talked about heat in a reaction, endothermic and exothermic. So we need to be able to use stoichiometry to do mole-to-mole conversions, use stoichiometry and molar mass to do mass-to-mass conversions. You need to be able to do the calculations of the limiting reactant, the theoretical yield, and the percentage yield. And of course, to all of this, you must always have the correct formula and ability to balance chemical relations.